Other aspect of quantum measurement, up to now, I considered ideal quantum non-demolition measurement just in the standard framework of the application of the postulate of quantum mechanics, just by applying projection to the atomic state. And now I will look a little bit into more details of the description of the connection between microscopic quantum systems and macroscopic world where you find measurement apparatus. And so the topic is the discussion around Schrodinger cat and their decoherence. So let me just briefly remind you what we learned in the first lecture. So the first lecture was devoted to the resonant coupling and the description of the coherent energy exchange between the atom and the cavity. And at that point, we already saw one example of preparation of Schrodinger cat state by making the resonant interaction of an atom, of a single atom, with a coherent field injected in the cavity containing like 13, 14 photons. Then I described the quantum non-demolition measurement apparatus, the non-destructive photon counter that we build out of circular Rydberg atoms, probing a microwave photon stored in a high-Q cavity. And so we have seen this picture of quantum jumps and projection of the quantum states occurring in this experiment. Yesterday, I talked about one application, which is quantum feedback. And I would like to mention one part of the lectures that I will not cover in the oral presentation, which is the analysis of the quantum trajectory in terms of what we call the past quantum state formalism as introduced by Klaus Malmer. So this formalism is a formalism providing the best possible estimate of the quantum state at a given time, knowing not only the past, all the measurement before time t, but also knowing the future. And it may be strange to you to kind of estimate the state at a given time knowing the future, because in principle, by definition, you don't know the future in advance. But the sense of this analysis is that once you have realized all the experiment until the end, then all the information you collected is eventually useful in order to get conditional probabilities, for example, of having n photons here, knowing not only this measurement result, but also taking into account the measurement results, the information obtained after time t, which, of course, is correlated to the information is connected to the state at time t. So there are correlations between that and that, which means that if you know that, you can have a better knowledge of the estimation of photon number distribution at that time. And indeed, an example of that is the case where the measurements project the field on vacuum. And as I told you, vacuum is kind of ambiguous with respect to 8 photons in the cavity because the measurement is performed modulo 8. And sometimes you have a wrong vacuum. And this is revealed by the future. If you project the field on the vacuum state, and it is not vacuum but 8 photons, then you see an abrupt jump in the future between 0 and 7. And then 7 cascade down to 0. And if you see this in the future, you know that indeed this 0 was not a 0, but it was a 8. So it's kind of intuitive way to feel that knowing the future tells you something about what is the state at that time. So Klaus Malmer developed a quantum formalism for having this kind of optimal estimation of the quantum state at a given time, which is based on a combination of an object that you know, the density operator describing the field at time t, and another operator, the so-called effect matrix, which is constructed backward by using the measurement result and starting from an initial state, which is not the initial state of the experiment, but which is basically a state with a priori no knowledge, so a probability distribution which is flat. So if you want to learn more about that, you can look at the lecture notes. So I have left the slides about this in the lecture note, and I would be happy to discuss eventually with those of you which are interested by this formalism, which is very efficient to have much less noise on this kind of quantum trajectories. So today I will rather focus on the problem of the Schrodinger cat and its link to quantum measurement theory, because this problem is interesting not just as a kind of funny academic problem, but it's intimately related to the properties of quantum measurement theory. So let me first remind the general context of quantum measurement, and I have presented this figure already. So up to now, I was focusing on this left part on this drawing, representing the scheme of indirect measurement in which two quantum systems interact according to Schrodinger equations. So here, the two quantum systems are supposed to be isolated and to perform some unitary evolution, which leads to entanglement between the two systems. And then I just assumed I measure this by applying the measurement postulate, and I check how kind of, and I calculate which kind of information I learn about system A when I measure system B. So now I will look a little bit more into the details of what happened in the measurement apparatus. So I'll try to build a quantum mechanical description of the measurement apparatus evolving according to Schrodinger equation, and try to see how an important ingredient that I did not explicitly consider when just applying projection postulate plays an important role in a quantum measurement. So the very strong difference between the red circle here and the black circle there is that here the system is supposed to be isolated, whereas when you consider measurement apparatus, the number of degrees of freedom becomes so large that it is always, the measurement apparatus is always somehow coupled to the rest of the world, which means that intrinsically this part of the system is dissipative, and dissipation is not just in the Schrodinger equations, and we'll see how it shows up in the formalism. So our goal today is to build a more complete and fully quantum model of the detector, including dissipation, which is a very important ingredient in quantum theory. So this is illustrated by this very famous cartoon by Wojciech Zorek. So I would like very much to mention his name because he played a prominent role in the introduction and in the formalization of the role of environment in a quantum measurement, which have to do with the transition between the quantum world, where in principle cats may be at the same time in superposition state of dead and alive state, and the classical world where everybody knows without even learning physics that cats are either alive or dead, but not both. So let us come back to the original quantum, the original picture introduced by Schrodinger for the Schrodinger cat problem, which is related to what happened when you measure a microscopic particle. So Schrodinger took the case of a radioactive particle, which is measured by some detector of particle detecting disintegration, eventual disintegration of this radioactive atom. And then, you imagine some system where a hammer breaks a bottle of poison and kills a cat. So you put this machinery into a box and you wait for some time. And you wait indeed for a time until which you have a decay of the quantum particle. So at a given time, if you know the lifetime of radioactive particle, you expect that you have a probability 1/2 that the particle disintegrates and 1/2 that nothing happened. And as a consequence, the cat has a probability 1/2 to be either alive or dead. But what you assume is that this box is completely isolated and that the evolution into the box is just described by unitary evolution as a consequence of the Schrodinger equation. So if box is isolated, you expect that after half-lifetime, you built in the box a quantum superposition, a coherent superposition of the two eventualities of this experiment, either no disintegration, and the cat is there, still happy, or disintegration. And that's just what tells Schrodinger equation. Of course, this is not in accordance with our everyday light, or everyday experience. And indeed, one important property of this state, it is that it's a fully entangled state, a maximally entangled state between two systems, the atom and the cat state. So we don't see it in the everyday experience. Then one question is, does this special vector of the Hilbert state really exist? And I think it's more interesting to formulate the question in a more pragmatic way by asking, can one perform an experiment, not a thought experiment, but a real experiment, in which one can demonstrate quantum interference between the two components of this superposition? That's the real physical formulation of this question. Does this state really exist? Is there an experiment demonstrating quantum interferences between the two components of the state? And of course, this problem is not just an academic problem. And indeed, fundamentally, the problem has nothing to do with cats. Schrodinger puts the cat in the game just to make it more demonstrative, maybe. But basically, fundamentally, the problem is related, this problem shows up in any kind of quantum measurement where, indeed, the interaction between the system and the measurement apparatus, if isolated, should lead to a quantum superposition of not only the quantum system, but the measurement apparatus, eventually giving a superposition of result, which is entangled with the atomic state. So if you just take into account the unitary evolution of quantum theory, you have to consider that unitary evolution produces this kind of unphysical state. And so the goal today is to study this kind of state and to find a quantum description, a quantum model explaining why they are unphysical and why it becomes more and more difficult to observe quantum interference between the two components of the Schrodinger cat state as the cat becomes bigger and bigger and closer to the macroscopic world. And for this, we will build an experiment, not with a cat, but with a mesoscopic object, which plays the role of a matter, and whose size can be varied from very small to very large to try to observe transition between quantum superposition and actual results of classical measurements. So let me add a few comments about these states. Indeed, about this statement that Schrodinger cat states are unphysical. And what I would like to mention is the answer of the founding father of quantum theory, because Schrodinger presented the example of the Schrodinger cat not as a contradiction, as an internal contradiction of the quantum theory. His goal when he introduced the cat state was just to say, to show with a demonstrative example that obviously, and this obviously was kind of obvious for the founding fathers of quantum theory, obviously unitary evolution should not apply at the macroscopic state. So it was clear from the point of view of the founding fathers of quantum theory that Schrodinger equation holds at a microscopic scale, and that at some point it does not apply anymore. And then the formalism say apply just projection postulate. So for Schrodinger, there was no point. The answer was obvious. This state is ridiculous, does not exist, because you should not apply Schrodinger equation at macroscopic scale. But then the discussion is, okay, where is the border? At which point do you decide that the system becomes macroscopic? And then the discussion becomes interesting. And that's the topic of the lecture. So one point, one can already mention it, is that this state indeed is eligible mathematically in the Hilbert space described in the system. But physically, we don't like it. And so we have to find a way, a physical mechanism, which tells us which kind of states are eligible in the Hilbert space and which kind of states are not. And that's the aim of the decoherence approach introduced by Zurek. And the dissipation plays a very important role in this decoherence mechanism. So indeed, I will look, my point of view now will be to look at this with a real experiment by constructing a system where a meter can be controlled and the size of the meter can be controlled to see at which point the quantum superposition states, the Schrodinger cat state, becomes a classical meter state. And of course, the tool will be the use of a small field stored in a cavity as an atomic state measurement apparatus. So indeed, in this point of view, I will kind of exchange the, I will have a point of view where I will exchange the role of the meter and the object which is observed. Up to now, I was using atom to observe a field in the cavity. And now I will construct a model where the field in the cavity and a quasi-classical field injected in the cavity plays the role of the meter of the atomic state. And what is interesting is that a small coherent field in the cavity have its size, which can be adjusted by just changing the strength of the coupling with an external source. And then this object is a mesoscopic object whose size can be varied continuously from vacuum to large coherent state in the cavity. And I will show that this coherent state can be used as a needle of a meter measuring the atomic energy, the atomic state in the cavity. So now the system under observation is one atom, and the meter is a classical field, a quasi-classical field stored in the cavity. So let me come back to the properties of a classical field I already mentioned explicitly. So these quasi-classical states were defined as eigenvector of the destruction, the photon destruction operator. Here again, I have introduced the explicit development of a coherent state on the photon number basis, where alpha is the parameter defining a given coherent state. It's a C number. Any C number is eligible with some amplitude, which corresponds to the dimensionless complex amplitude of the field, and a phase, which corresponds to the classical phase of the field. So I already mentioned the photon number distribution, which is a Poisson distribution. And now I would like to introduce more precisely a kind of symbolic representation of quantum state in the field in the complex plane. So if you are dealing with a classical field, you can write its amplitude using complex notation. And so just forget about quantum mechanics. It's very common in classical electromagnetism to represent the amplitude of a field by a vector in the plane. That's the so-called Fresnel vector, if you know this. Or if you use a dimensionless vector to represent the field amplitude, then the Fresnel plane can be considered as a complex plane. And you can represent the amplitude of any classical field by a dimensionless C number that you have to multiply by a constant homogeneous to electric field to have the complex amplitude of the electric field in the complex plane. So this complex plane, the two axes, has the real and imaginary part of the complex amplitude of the field. So I'm sorry, here the Greek letter disappeared for some reason. So modulus of alpha is the length of this Fresnel vector, and the phase phi is the argument of alpha corresponds to the phase, what we call the phase of the classical field with amplitude alpha. Then, in addition to this representation of the classical part of the field, its average value, quantum mechanics tells you that the amplitude of a quantum field is not perfectly well defined due to Heisenberg uncertainty relations, which means that the end of the vector points is kind of fuzzy and points here in a circle revealing the amplitude of uncertainty of quantum fluctuations of the field. And in this dimensionless space, where the complex amplitude square have a dimension of a photon number, the unit, the magnitude of the diameter of this fluctuation circle is about 1. Indeed, you can see from this formula that for any value of alpha, you have a quasi-classical state, which means that there is an interesting special case which corresponds to alpha equals 0. So alpha equals 0, which is vacuum, is a quasi-classical state, which means that these fluctuations for alpha equals 0 are just corresponding to vacuum fluctuations. So you already know about that. Then a quasi-classical field is a field whose fluctuations are indeed with the same magnitude as vacuum. And indeed, in this sense, quasi-classical states are the quantum states you can construct to mimic some finite complex amplitude of the field having minimal quantum fluctuation. And minimum cannot be less than vacuum fluctuations. So fluctuations of coherent states are the same as vacuum, except that they are translated at the top of a vector representing the average field in the cavity. So I would like also to introduce an operator which is very useful and which generates this coherent state from the vacuum. So it's a unit operator, d of alpha, which can be expressed as a function of creation and annihilation operator. And this is the exponential of alpha times a dagger operator minus alpha square, alpha complex conjugate times a operator. So this operator, you can check easily, it is unitary operator. And when you apply d alpha over vacuum, you get the coherent state alpha. So mathematically and formally, it's very interesting to use it when manipulating a coherent state. So indeed, this operator, it is also easily shown that the evolution, that's a physical evolution operator, describing the coupling between a classical source, represented by a classical current, coupled to the field mode in the cavity. So if you take an Hamiltonian with a coupling between this current and the vector potential of the field in the cavity, and you resolve the Schrodinger equation, the unitary operator, the evolution of the field, corresponds to this displacement operator with alpha of t proportional to time. So like alpha 0 times t, and then a rotation at a frequency omega t. So this operator is useful, and it is interesting because it has a very simple geometric interpretation. In the complex plane, this operator just produces a translation by a vector alpha, and it produces a translation not only on vacuum, but on any state. So this displacement alpha applied over beta will lead to alpha plus beta, which is a new coherent state, which is the interference between the two complete amplitude with some phase factor here that I will not explicitly write, but which depends on both alpha and beta. As a global phase factor, we don't care very much about it. So we have this tool, this displacement operator, and we have a simple way to realize it by switching on a classical source coupled to the microwave cavity, which will produce a translation of the state without changing the shape of the fluctuations. That's an important picture. So let us consider this object, and this object, represented in the complex plane, is represented by an arrow, which is nothing else than the needle of a meter will point in different direction in the experiment, depending on the atomic energy on whether the atom interacting with the cavity is prepared either in E state or in G state. So let us consider now the interaction of this quasi-classical state with a single atom and assume that this atom is prepared in state E. So the initial state of the cavity is prepared by this source, which produces a displacement, and I choose here the origin of phases so that the initial field has its phase along the real axis, the real part of alpha axis in the complex plane. So let us now make one atom cross the cavity. What is the evolution of the field? So I could write Hamiltonian and resolve the evolution. So indeed, we can intuitively describe the result of the non-resonant interaction with the cavity in the following way. So here again, I choose non-resonant interaction so that the atomic state is not changed by the evolution. I want a non-destructive measurement. I want to build a non-destructive measurement apparatus of the atomic energy as a result of interaction. So if interaction is non-resonant, energy conservation means that the atom cannot absorb emit photon, just as before. And so the atomic state remains in A. What about the field? Indeed, the field has its phase, which is just shifted without changing amplitude. So amplitude does not change because there is no energy exchange. But the phase can be affected. And in order to understand this, you can imagine that a non-resonant atom is a kind of very teeny, it's the limit of a microscopic dielectric, a microscopic piece of dielectric which crosses the cavity. This dielectric is transparent because the atom does not absorb energy. But it has some polarizability. So it has some index of refraction. So it can be fun to talk about index of refraction of a single atom. But you can figure out that the atoms there crossing the cavity have its polarizability just phase shifting the wave, the optical wave propagating between the two mirrors. And this phase shift amounts to change the optical length of the cavity. So it transiently changes the frequency resonance of the cavity. And as the field is not dissipated, its frequency will follow adiabatically the motion of the atom, so the variation of the optical length of the cavity. And as a result of variation of this optical length, the field will accumulate some phase shift related to the interaction time with the atom. And then, and this can be formalized easily, the current state is just phase shifted with respect to the initial one. So here is phi, the phase shift induced by a single atom on the field. So how big is this shift? Because one atom is not big, it's not much, and with usual atom you expect very small phase shift. So the atom is not that small because it's a Rydberg atom, so it's a large dipole with a size n squared times the size of hydrogen atom. It's a large antenna with a large polarizability. And indeed, it appears that this phase shift is half the phase shift per photon I already considered. So with a phase shift per photon of pi, as considered when detecting 0 or 1 photon, this phase shift is macroscopic. It can be as large as pi over 2. Then the rest of the story is straightforward. You can also eventually inject the atom in the other state J, and it appears that if you have two level atoms, the polarizability of the upper state has opposite sign as compared to the polarizability of the lower state. This is a well-known result for two-level systems, which means that the phase shift induced by atom in G is just the opposite as in E. And you see that as soon as phase shift is larger than the fluctuations, you get two distinguishable directions for the needle of the meter. And so as soon as the phase shift produce a phase shift larger than phase uncertainty of this state, you have built, in principle, a good meter of the atomic state. The interaction leads to an entangled state between the energy of the atom and one classical variable of the field, of the quasi-classical field, which is its phase, which points either in direction phi naught or minus phi naught. So here you have a pointer whose size can be varied by injecting more and more photon in the cavity. And you see that interesting situation where a classical, quasi-classical characteristic of a field, its phase, can be used to measure the quantum state of one atom. Of course, that's not the end of the story, because here we are still dealing with an isolated system. The field in the cavity, because the cavity is very good, is completely isolated from the environment. So we expect to effectively have prepared an entangled state, which is not yet a classical measurement result. So we'll now go to the next step. So here, this slide just depicts the role of the matter played by the field. And so this field can be considered as a matter pointing at the same time in two directions, which are correlated with the atomic state. And that's our version of the Schrodinger cat state. And now we go to the next part, and the main topic of this lecture, which is to introduce dissipation, to introduce the role of the environment to describe the fate of this Schrodinger cat state. So what about coupling to environment? So I will not develop formally a full lecture about dissipation in the field. We use the density operator. We have to use the density operator formalism in order to describe the field state, or more generally the entangled atom field state. And indeed, the general method for describing dissipative evolution of the field state due to energy damping, so this corresponds to energy damping, corresponds to this master equation, which, gives the expression of the derivative of the density operator of the field, so if you write it, and as a function of, indeed, basically one parameter, which is the cavity damping time, the energy damping time of the cavity, which is the exponential time constant of this energy damping process, and the operator A and A dagger. So with a part here, which is an anti-commutator, and this part, which has this form. So that's the master equation, which is very well established, describing quantum mechanically the evolution of a field submitted to damping due to energy losses. And the physical result when solving this equation is that there is a time constant characteristic of the lifetime of this kind of state, which is a so-called decoherent style, which scales as the cavity damping time divided by the photon number in the cavity. So that's the important result of the evolution of the cat state under the effect of this master equation. And now I'll try not to make a full rigorous mathematical demonstration, it can be done, but to give you a simple model of decoherence leading to this result. So let us consider not only the cavity, where the atom interacts, but the Schrodinger cat state prepared in the cavity. And now we'll explicitly give a model of the environment by saying that, okay, energy losses can occur for many different reasons, either absorption in the mirror, diffraction on the border of the mirror, but all these losses could be modeled as if the mirror was kind of transparent with a very, very small transmission, and that some photons from the cavity, instead of being absorbed, are just leaking into the outside world, which is the environment, and which can be modeled by a very, very large cavity, whose size have to be set to infinity. So the evolution indeed starts with, let's consider first not a cat state, but a coherent state with the environment in a vacuum state. So what do we expect from the Schrodinger equation, from the coupling between these two systems? One mode here in the cavity with many, many modes in the environment. Indeed, that's a problem. Oh, I should not be there. So that's a problem which can be solved exactly because it's basically a problem of coupling between harmonic oscillators. So some oscillators are resonant, some others are not, but you can solve the Schrodinger equation for this problem. And the important result is that as a function of evolution, if this state is coherent and the other is vacuum, the evolution basically consists in keeping a coherent state here. So you can demonstrate that the coherent state remains a coherent state in the cavity with amplitude which is exponentially damped. I'm sorry, there should be a factor 2 here because the energy is damped with damping constant T cav, which means that the amplitude lives 2 times longer because it has to be squared. So here is the decay of the average amplitude, and the important result is that the field in the cavity remains a quasi-classical state, a coherent state, whose amplitude diminishes as a function of time. And then, indeed, energy conservation means that some field should grow up in the environment. And the field which grows up is not a single coherent field, but a tensor product of many coherent fields in many different modes, with the main amplitude is the mode in the mode with the same frequency as the mode alpha. So I represent the environment state, indeed, by the growing of a classical, again, a classical field with basically the same frequency as the cavity frequency. And then this field, indeed, will play an important role in the sense that it carries some information about alpha in the cavity. And the information is that the phase of beta is the same as the phase of alpha. So when you have losses, when the mirror broadcasts some information outside the cavity, it radiates a field with the same phase as the source. And there is information about the phase of the source encoded in the phase of beta. So that's the important point, because the leak of information in the environment plays an essential role in the description of decoherent. So an important property also of the evolution here is that there is not yet some entanglement. The state remains a product state. And indeed, that can be taken as a definition of a quasi-classical state. Indeed, the quasi-classical states are the only one which evolve in this process without becoming entangled with the environment. And in this case, they are kind of very robust quantum states. They remain pure states as a function of evolution with time, and this can be taken as a definition of a coherent state. They are the only states which have this property. If you have any other quantum superposition state of the field, it becomes entangled with the environment. And indeed, in the framework of decoherence approach of Wojciech-Zurek, robustness with respect to entanglement with the environment is kind of a good definition of what the classical state is. So that is an important property. So let's go to the end of the story. Now we'll consider the decay not of a single coherent state, but a superposition state of 2 coherent states. And here I don't care about the atom, I just care about the property of the superposition state of the field, which is closely related to the decay of the superposition state, additionally involving the atom. So the cat state now is supposed to interact with the environment, which is again assumed to be initially in vacuum. And so the evolution is just a linear superposition of 2 of these evolutions, one with the state alpha plus and the other with the state alpha minus, because the cat state is assumed here to be a superposition of these 2 coherent states. So as a result, you are led to this quantum superposition with the growing in the environment of 2 small coherent fields with different phases, each of them being correlated to one of the alpha plus and alpha minus component of the cavity Schrodinger cat state. Well, you see entanglement here is growing, and what is the consequence? Indeed, the consequence is once you are just interested in the properties not of the environment plus the system, because the environment is losses, so you will never measure what happened in the environment. You have, for making prediction, just to keep the information about the field in the cavity. And formally, this corresponds to the fact that you will introduce the density operator of the field in the cavity for only the cavity mode by tracing over the environment variable. And when you trace over one part of an entangled state, if the two states here are orthogonal, so the scalar product is 0, then you get a diagonal density matrix for the state of the field remaining in the cavity, which means that coherences are lost. They are lost as soon as these two states become orthogonal. And indeed, the decoherence time of the Schrodinger cat state is related to the time, is precisely related to the time it needs so that beta minus and beta plus becomes orthogonal states. And that's the definition of the decoherence time, which corresponds to the time scale at which this superposition state, which is entangled, leads to a completely mixed density operator for the field remaining in the cavity, a statistical mixture or alpha plus and alpha minus. So the important point, an interesting point, is that it's easy to calculate the evolution of this scalar product, the magnitude of this scalar product as a function of time. And you can estimate it for a simple energy conservation argument. Indeed, beta you can calculate from energy conservation. Yeah, is the expression modulus square of beta plus modulus square of alpha of t should be equal to modulus square of alpha 0. So you replace alpha of t by alpha 0 times exponential minus the exponential decay. So here again, there should be a factor 2. Here it's energy, so here the factor 2 is correct. And so you find that beta at t equals 0 is 0 and increases as a function of time according to this expression. And for short time scale, I can use an expansion of this for short time scale, beta is growing linearly with time. So energy beta square is growing linearly with time, which is an explicit expression of the modulus of beta of t. Then from quantum optics formula, you can find the expression of the scalar product between two coherent states. So it is expressed here. It depends not only on the modulus square of beta, but also on the relative phase between the two beta fields, which is 2 times the phase shift induced by a single atom I introduced in the first slide. So you have the expression of this scalar product. You have the expression of beta square. And if you take the maximum value of phi naught equal pi over 2, you can deduce from this the time scale at which the scalar product becomes 0. It corresponds to basically beta square of the order of 1. And beta square is of the order of 1 as soon as time is of the order of the cavity damping time divided by the average photon in the cavity. As you can see from this expression, if you express this equals 1, it means that times have to be of the order of t cap divided by modulus square of alpha 0, which is the average photon number. So here you get an expression in this simple bundle of the decoherence time, the time needed for a quantum superposition of alpha plus and alpha minus to become a statistical mixture. And what is interesting here is not only the quantitative expression, but the physical interpretation. The statistical mixtures happen, decoherence happen, as soon as there is enough information on the environment so that these two states become distinguishable. And here you can use a complementarity argument in order to describe decoherence. As soon as you have which path information about the phase of the phase field encoded in the environment, you do not expect any more quantum interference between these two components of the state. So that's an argument that Bohr could have formulated using the complementarity concept. So decoherence corresponds to leak of information which encodes which path information about the phase of the field into the environment. And as soon as this information is encoded, you do not expect quantum interference between these two components, which means that the Schrodinger cat does not exist anymore because you cannot observe consequence of this superposition and decoherence is done. So then let me finally comment the more quantitative expression of the decoherence field, including the dependence with respect to the relative phase of the two components of the Schrodinger cat state, by introducing an important parameter in the complex plane, which is the distance between the two field components. So here I have a drawing of one component of the Schrodinger cat state with phase plus phi, the other with phase minus phi. And indeed, the decoherence time, so you can rigorously demonstrate that it is 2 times the cavity damping time divided by d square. And d square has the same magnitude as the amplitude of the field, so it's kind of homogeneous to a photon number. And d square is the size of the cat in unit of photon number. And then just a simple geometric calculation tells you that d square here is 4 times the sine square of the angle phi. And then you understand that as soon as your meter becomes a classical meter, so goes into the classical world by having more and more photons, it becomes more and more difficult to observe measurements sensitive to Schrodinger cat state, because decoherence is faster and faster with bigger cats. And if you consider fields not with 1, 10, or 100 photon, but 10 to something as radiated by a classical source, you basically, in practice, have no chance to observe a quantum state superposition of the field within the decoherence time scale, which becomes so short that it becomes shorter than any measurement time in the experiment. So then I will just have comments about this model, about the role of the environment. I'm not sure that all slides are in the right. Okay. Okay. So that's what I said about the physical origin of the information, which is leak of information. And indeed, when doing the usual, when applying the usual interpretation of quantum mechanics by applying the collapse approach, which is included in the postulates, indeed, one can consider that this approach, introducing collapse, is indeed a way to have a shortcut of this to this interpretation of quantum measurement in terms of decoherence by indeed hiding the role of the environment by using a much simpler thing, which is a collapse postulate. And indeed, as the decoherence approach needs some formalism and mathematical formalism development, if you want to teach quantum mechanics to people, it's much easier to make them accept the recipe, the collapse, than to try to explain its origin and its relation to a complex, which is the entanglement with the environment. But the heart, I think, of the justification of this collapse postulate is the fact that if you can describe quantum mechanically the interaction between the environment, quantum theory, which is an information theory, tells you that information is leaking in the environment, and that leaking of information produces the decoherence, which in shortcut is just represented by this collapse of the state in the usual quantum theory, which tells you that once you have performed a measurement, you don't deal with superposition, you choose one of the results, and you choose the one which corresponds to the measurement result. So one question which can be considered maybe not just as a physical question, but which enters eventually the field of metaphysical questions, is, does it solve the measurement problem? So then I think that the answer depends on what you call the measurement problem, and I'm not sure that what is called the measurement problem has an objective definition. So I think that the answer may be no or yes, depending on what you call the measurement problem. And indeed, if the problem consists in telling how or why nature chooses randomly one classical state, I think that the decoherence approach does not explain why quantum mechanics is a statistical theory. It does not explain which microscopic physical mechanism chooses a result in a given experiment. And indeed, quantum theory tells you that, okay, this mechanism is completely not accessible. Randomness is fundamental. So I think that my point of view is that explaining with some equation the randomness of quantum theory is kind of hopeless for me. The statistic characteristic of quantum theory is given from the beginning, and I don't know what means quantum theory without putting the statistics a priori. So then I think a more optimistic answer to the decoherence approach is that it solves the measurement problem if one a priori accepts the statistical nature of quantum theory. And I think once you accept this as a first postulate, then the decoherence approach tells you that the quantum theory is a self-consistent theory. You cannot find contradiction, and you understand why the probability of measurement results does not involve Schrodinger cat state as soon as decoherence occurs. So I think that's what we learn from this decoherence approach. So a little bit more formally, what we get from this approach, as I already mentioned, is a definition of what is the so-called pointer basis of a measurement apparatus, of meta. And this concept of pointer basis, again, was introduced by Zurek. So the pointer states, one could take an intuitive definition, which is in practice a kind of very good definition, which is, okay, the pointer state basis is the ensemble of classical states of the matter. And if we have a measurement apparatus in front of you with a needle, I think that everybody will agree that the classical states are the states where the needle has a well-defined position and is not in a fuzzy state superposition of all results. Okay, this is fine. Everybody agrees more or less about what is a measurement. But what would be also fine is to have a kind of objective definition of what a classical state is, which does not depend on what I believe, because I would like that a physical theory does not depend on my opinion about what is classical and what is quantum. And I think that the decoherence approach does this job. So when you consider the cat state involving these two states, atom either in E and G, and the field pointing either in one or in another direction, there is, according to Zurek and according to the decoherence approach, a kind of preferred basis, which is defined objectively by the form of the dissipation, by the form of the master equation. And there is a basis in which, after decoherence time, the density operator of the field becomes a diagonal density operator. And this can be taken as a kind of definition of what classical states are. And this has to do with the robustness of classical states with respect to entanglement I already discussed. So the classical states is the one which define the basis in which the density operator of the field becomes diagonal under the effect of relaxation. And the diagonal density operator, the statistical interpretation of a diagonal density operator, is a statistical mixture, a completely statistical mixture of different classical results. So that's, I think, an important byproduct of this decoherence approach. And indeed, when you have the diagonal density operator, you are just dealing with classical probabilities of having that state of that state. You see, you don't have probability amplitudes involved in this density operator. So that's the point concerning the principle. And now I will go into the experimental observation of this decoherence process. But maybe it's good to have a short break here to have questions about this first part of the lecture. So I know that probably all of you are not familiar with the density operator formalism, but I think it's very difficult to talk about decoherence without this object. But the model I gave with the classical field leaking into the environment was kind of intuitive, I hope, for giving some idea. Yes?
So there is part when you say that the phase of beta is equal to alpha.
Yes?
Is this an assumption? Or
no, that's a rigorous result. And it's kind of intuitive. You imagine that you have some oscillating field in the box, which is leaking to the outside, so optical field, radio frequency field. The field radiated to the outside is phase coherent with respect to the field in the cavity. If you have a laser, you have a phase which is well-defined in the cavity, and the field which leaks out of the cavity have the same phase. It cannot be, so it can be phase shifted due to propagation. That's just a trivial effect. So this is a goal. Okay, but when a photon given just one photon does not have classical phase. It's just fluctuation, one photon. So it's related to the fact that you have some phase information there, and this is not the case if you have a single photon state or n photon state. You need a coherent object so that the evolution is that simple, just a scalar product with two fields with the same phase. If you have a number state here, it leaks, but the leaking produces huge entanglement. Basically, if you have n photons leaking in an environment which is initially in vacuum, then the state is the sum over all photon number, 0 to n, with all the possible states with n minus n prime and n prime photons in the environment. So this is completely entangled, and there is the number state have no well-defined phase. So the classical phase is meaningless in this state. And so when I talk about classical phase, I'm really dealing with coherent state. Yes?
I didn't understand well what would be the environment, because the system is the atom and the cavity. And the environment is...
So the system is the atom. The meter is one mode of the cavity containing the current field, and the environment is the outside world, which is coupled to the field mode. Okay. And this residual coupling physically corresponds to loss of energy in the cavity. And I model this loss of energy by a semi-transparent mirror with a very small transmission, and then the field alpha leaks in the environment. So I assume here in the model a very clean environment. The actual environment is much more complex. It's all the atoms there which may absorb photons and change state, the electrons which can be shaped and hidden, photons which can be diffracted in many other kind of mode. But all this correspond to energy losses and can be modeled by this simple environment. And the modes in the environment are harmonic oscillators. They are quantized exactly in the same way as the field here. So you can here model the environment as a huge cavity whose size will go to infinity and write the harmonic oscillator mode there and explicitly write the coupling between all these harmonic oscillators. But the result has this form, the result of the evolution.
And could you explain again how to produce the coherent state?
So the coherent state, I explained at the very beginning that it is produced by using the displacement operator, which is unitary operator. So this is an evolution operator. What? In laboratory. So in laboratory, it's what I already did when injecting a field. I have a classical source, or a sensitizer that I can just buy, which is connected to a waveguide, and the waveguide emits microwave photon in the setup. And when a field originates from the sensitizer, a very good representation of the field radiated is a coherent state. So, because it's basically classical, and its fluctuations are really the minimal one, the quantum fluctuation. And then this field, which is radiated all around the cavity, coupled slightly with the cavity mode by diffraction on the border of the mirror. So a little bit fraction of the huge current field enters the cavity, and even just a fraction of the field enters the cavity. It can be shown that what enters the cavity produces a current state. Indeed, it's an attenuated current state, and attenuation preserves coherence of current state. So indeed, it's the easiest part. Having a 1 photon current state or 10 photon current state in the cavity, it's just you switch a microwave source. You have to calibrate it carefully, so you use the atoms to calibrate the photon number entering the cavity, and then that's it. Automatically, classical source, when attenuated and going into the cavity, produces a classical field. Okay? Yeah?
Sometimes in the master equation, it's important the things that leak from the environment, the system of the environment, but also what comes from the environment. Maybe as a coherent pumping.
You mean back action from the environment. So it depends on the environment state, but of course, all this is included in the formalism. But here, I assume that the environment is initially empty, so it could have thermal fluctuations. A more realistic environment contains blackbody radiation, which means that photons can not only leak into the environment, but photons may be injected by the environment. So all formula I gave can be generalized to take into account this kind of symmetric interaction. It's never symmetric because by construction, the environment is kind of huge system with many degrees of freedom, and it fixes the direction of the arrow of time. And dissipation is that average energy goes from the atom to the environment if you have energy in the cavity. Other question? Okay, so now I go to the experimental demonstration of this, basically the experimental preparation of a Schrodinger cat state and characterization of its decoherence. So here I present the first experiment we performed. So not the very best cavity I described yesterday, but with the first cavity which reached the strong coupling regime. And indeed, in this experiment, we performed kind of a partial characterization of the Schrodinger cat state in contrast with the next experiment, where we'll perform a full quantum characterization of the state of the cat. But I think it's interesting to start with a simpler experiment, which is indeed a 2-atom experiment. So here is the cavity, 2 atoms successively crossing the cavity, and basically the first atom will prepare the Schrodinger cat state in the cavity, and the second atom will probe this cat state and probe its coherence by kind of recombining the 2 components of the cat and trying to make them interfere. So more precisely in this experiment, the first atom was splitting the cat states in 2 components, and the second atom was just splitting again these 2 components, and as a result of this double splitting, you get 1 component which is again with phase 0. And basically we measured an atomic signal, so I don't want to go into the details, which is a measurement of the coherence between the two components of the cat state, and which is contained in a correlation function between 2 successive atomic measurements. So the point is, and what I like with this code, is that it shows how this coherence decays as a function of time, which is here in unit of cavity damping time, for 2 different sizes of the Schrodinger cat. And you see already on this signal an important feature of decoherence, which is that when the size of the cat, when the dimension, so the distance between these 2 components, as I defined, that I defined as the dimension of the cat state, the distance between these 2 components, when it is larger, the coherence is faster. And we demonstrated this feature in this early experiment realized in 1996, not with the best cavity, but with the one which have a quality factor of only 2 × 10⁸, and a single photon lifetime of the order of 200 microseconds, which was already the strong coupling regime. So I do not want to tell more about this first measurement, which was a kind of partial measurement of the density operator. It was sensitive essentially to the off-diagonal element of the density operator in the coherent state basis. And I will now focus on an experiment where we basically managed to fully characterize the state prepared in the cavity by fully measuring its density operator and representing it by the Wigner function, which is a nice object to represent single mode field states in quantum optics. So that's the topic of this part, the tomographic reconstruction, the full reconstruction of the state stored in the cavity. So what is the principle of the state reconstruction that we perform in the experiment? So the general principle is depicted here. You have a system with some unknown density operator. You have a set of observables. You perform many preparation of the state, many measurements. You get many measurement results. And then you try to find the best way from the measurement result to reconstruct the unknown state or the density operator of the system you measured. Indeed, you can see that each measurement gives you some constraint of the density operator. For example, the probability to find the result Gi, where Gi is a projector corresponding to measurement result I in measurement G. So you can calculate the probability of result of this measurement as a function of density operator. And the value is what you measured. If you have a large number enough, number of measurements, you get the probability, the measured probability to have a given result. So this gives you a linear equation on the matrix element of the density operator. And the naive way to reconstruct the matrix would be to have a large enough set of measurements so that you have a large enough set of constraints over the density operator so that it fully constrains its coefficients. And then you have to basically invert a matrix to get the matrix element of density operator. So this is simple, but this is not very efficient because of several reasons. If you have statistical noise, and in measurement results you always have statistical noise, you can eventually, the mathematical inversion of this set of equations can lead to unphysical matrix density operator with negative values on the diagonal that you don't like. So you would prefer a method which, by construction, gives you physical density operators. So if you have too many measurements, again, due to noise and statistical noise, your matrix may be non-invertible. You have too many constraints which are incompatible between them. So you have to find something better than just inverting a matrix. And indeed, what we'll do is to use the measurement in a better way. So which kind of measurement can we use to extract information about the density operator of the cavity? Indeed, we use the information we get by quantum non-evolution photon counting. That's our best way to measure the field state. So that's a very good way, but it only provides information about the diagonal elements of the density operator. And of course, you need also, if you want to reconstruct the quantum state, you need also information about the off-diagonal element of the density operator. But indeed, there is a trick just to convert off-diagonal elements into diagonal elements. And the trick is very simple. It's the displacement operator I already mentioned. So if you have an arbitrary quantum state of the field and apply displacement operator in the complex plane, so your arbitrary state is here represented by a kind of arbitrary shape, you can just translate it in the complex plane by applying displacement operator d alpha that you can physically realize easily. And this operator is perfectly well determined as soon as you have a good calibration of the complex amplitude alpha. Which means that after this displacement, you have a new density operator that you know exactly how to compute as a function of the initial one. And it's just linear relations. And it means that you know where you are. And the important point is that the density operator mixes diagonal and off-diagonal elements of the initial density operator. Which means that if you measure by Q&A photo counting not the initial state but the displaced one, you will get information not only on the diagonal of the initial state but also on the off-diagonal matrix element. And then the characterization of the field rely on measuring on quantum non-demolition photon counting of the state after many different displacements with many different amplitudes, which corresponds to measuring many different observable, many different non-commuting observable, giving different information about the density operator. And in the end, we reconstruct the density operator from that. So technically, how do we do the reconstruction? So I already mentioned the fact that the direct fit of the density operator on the measurement data is very sensitive to noise and leads to problems like non-positive density operator. Then you have several algorithms which were developed in quantum optics, which by construction find an object which is a density operator. So there is the so-called maximum likelihood method, maximum entropy principle method, and basically which are the main method, which estimate the state on the basis of measurement result. And the interest of the second method, maximum entropy principle, is that it works, it provides you a density operator even if your set of measurements is not complete. If you don't have measured enough operators to get all the density operator matrix elements, then you can still get an estimation of the field operator, and maximum entropy chooses among all density operators which are compatible with the result, the one which maximizes the entropy. So it's kind of worst case estimate. So in our case, the number of measurements is large enough so that we completely determine the density operator. And then the two methods, maximum likelihood and maximum entropy principle, are equivalent. And maximum likelihood is in principle a simple method. It finds the density operator which maximizes the probability of the observed results. So you have a set of observed results. You have a density operator. From the density operator, you can calculate the probability to get what you observe, and you choose the density operator which maximizes this probability. So that's what we do for state estimation. So in the experiments, we proceed in an iterative way. We prepare the state to be measured. We measure the photon number non-destructively after many different displacements. Indeed, we take a large ensemble of value of complex amplitude alpha. We measure the photon number distribution for like 400 to 600 points in the complex plane. So we really sample the complex plane with a very small grain. And then in the reconstruction I will present, we use the maximum entropy method in order to minimize a priori information about the field and having kind of worst case estimate of what is the field state in the cavity. And then from the matrix element of the density operator, we calculate the Wigner function of the field in the cavity. So what is the Wigner function? Indeed, okay, so that's a representation of the field state in the complex plane. And here you see the Wigner function for a coherent state initially injected in the cavity. So you see that from the reconstruction, we can compare the reconstructed state to what we know. We know a priori the amplitude injected in the cavity. And you see here that the method of injection of a coherent state in the cavity works very well. And if you characterize the field injected with a classical source, it fits to coherent state with a fidelity of 98%. So it means that injecting a coherent field with a coherent source really produces a coherent field in the cavity. So we applied the reconstruction method to number state, and basically we use the quantum non-demolition measurement approach I presented in order to prepare number state by selection. Once the quantum non-demolition measurement tells you have 2 photons, if you believe it, you start state reconstruction. And here are the quantum state reconstruction for number states ranging from 0 to 4 photons by the reconstruction method I just mentioned. So you see that here is the density operator. So you see the high purity. You have a feeling of the purity of the prepared state in the cavity. Vacuum is very good, so it's not a challenge to have a very good vacuum. But if you have vacuum, and if the machine reconstructing the state does not know it a priori, from the measurement, it reconstructed this vacuum with a fidelity of 99%. And the difference between 1 is eventually not related to measurement error, but it may be related to the residual presence of 1 blackbody photon in the cavity from time to time, which is responsible of this small yellow square here. The rest is kind of noise. So 1 photon, very pure, 2 photons, 3 photons, very pure. You see here that 4 photons is reconstructed with a slight decay to 3 photons because the measurement used for reconstruction takes some time. And if you have 4 photons, it may already start to decay during the measurement time. And you see here on that it's more difficult to prepare a characterized larger number state because they are more subject to decoherence, as I already mentioned. Then the second line is a set of Wigner function representing in the complex plane these various quantum states. So the Wigner function is a quasi-probability distribution, so I don't want to introduce it formally, that you can interpret as a probability distribution of the field, complex field amplitude, if the field is classical. So you see that vacuum as a Gaussian Wigner function, which corresponds to the size of the Gaussian, corresponds to the size of vacuum fluctuations. So this is kind of a picture of the vacuum fluctuation represented on the Wigner function. So if you consider a coherent state, the Wigner function is the same Gaussian as vacuum, but not anymore centered on vacuum, but on the classical amplitude, the classical complex amplitude of the field. And for other states, which are non-classical, Wigner function becomes quantum, have negative values, so you cannot interpret it as a probability. So we say it's a quasi-probability. And so for 1 photon, it has a strong negative peak at the origin. For 2 photons, it has oscillations with negative values of a ring here. And the larger the photon number, the more ring you have in the Wigner function, as you can see here on this picture for n equal 4 photons. So let us now go to the Schrodinger cat state. So the Schrodinger cat state here is prepared by the process I depicted in the first slides. You send an atom non-resonantly interacting with the cavity. You apply a power 2 pulse to prepare the atom in a quantum superposition of E and G. And you apply the interaction, non-resonant interaction, which causes phase shift of the cavity field depending whether the atom contains is in E or G. And you prepare in this way the Schrodinger cat state. So that's the first part of the quantum non-demolition experiment. And what I do to completely characterize the field, I will finish the story exactly in the same way as in the quantum non-demolition experiment. I apply a second pi/2 pulse to the atom, and I detect it. And what is the result of this detection? So the pi/2 pulse here transfers E to E plus G, G to E minus G, and in the end, when I detect E, I have a contribution of both these 2 components of the wave functions. That's the way to get a quantum interference between the 2 components of the Schrodinger cat state. And when detecting the atom either in E or G, the field state is projected either in the superposition of the 2 fields with different phase within plus or minus. So that's why I discussed in the decoherence model, the simple model I presented before, not the decoherence of the entangled state, but the decoherence of this superposition state, which is not entangled, so it's not a genuine Schrodinger cat state, because entanglement is an important ingredient in genuine Schrodinger cat state, but it's a case containing the same kind of coherences with respect to the field state. And once prepared, that's this state that we characterize and that's the decoherence of these states that we measure in the experiment. So in the experiment, we set the parameter so that the phase shift per photon is pi, so that the two components of the field involved in the superposition have opposite phases. And if the atom is detected in E, we have a plus sign here. And if you look at the photon number distribution of this state, as a consequence of interference between probability amplitude, these states have only even photon number. So we call it the even cat state, whereas the other state has only odd photon number, and we call it the old cat state. And depending on the detection result of the atom, we know whether we have odd or even cat state. Of course, if we trace over the atom, we just have a statistical mixture, and it's not anymore a Schrodinger cat state. So here is a representation of the raw data of the experiment. So you have the complex plane. The dots represent the amplitude of all the displacements we perform for measuring the cat state by quantum non-demolition photon number after preparation of the cat state. And indeed, the atomic signal as a function of alpha looks very much like the Wigner function. It's like cut in the Wigner function, but I would not say too many details about this. Here is presented the result of the reconstruction by maximum entropy method. So that's the density operator for something like 2.1 photon injected on average in the cavity initially. So this is not very demonstrative, so that's why we prefer, so this you can see basically the parity of the photon number, but it's much more demonstrative to go to the Wigner function representation of these states. It's very nice, it's better because in the Wigner function, you can distinguish the classical and the quantum component of the superposition state. So for those of you who want the formal definition of the Wigner function, it is written here as a function of the density operator. And it is, I like this expression. There are many equivalent definition of the Wigner function. I like this because it's a trace of density operator times some operator, which is an observable. If you look at this, the observable, this is a parity operator. E dagger to I pi is a parity operator, which has a value depending on the parity. And then this is displacement. So basically, it's the average value of displaced parity operator. So here is the result. The Wigner function of the cat state reconstructed for a field with a bit more than 2 photons in the cavity is here. And the principal components are the 2 red dots here, which are resulting, are the trace of 2 classical components, 2 nearly Gaussian peaks corresponding to the 2 opposite phase components of the field in the cavity. Then in between, you have oscillations, which are the signature in the Wigner function of the coherence of the superposition state. So you can nicely, with the Wigner function, isolate the classical feature of the cat state, the 2 classical components. You can identify the size of the cat by looking at this distance, and you can assess the coherence of the cat state by looking at the amplitude of the oscillations between the 2 classical components of the Schrodinger cat state. So then we perform this characterization for both the even and odd cat state by separately reconstructing them. And an interesting point is that if you average the odd and even cat states, it amounts to take the trace over the atomic detection, ignoring its results. You find not a cat state, but a statistical mixture. You still have the 2 classical components of the field, but you have no interferences at all in between, which means that this state corresponds to a state after decoherence, where the coherence have been killed. So we can estimate the fidelity of the state with respect to the expected one, so it's kind of high fidelity. And here are the ideal Wigner function we expect from a model of the experiment taking into account imperfection, which is really very similar to the reconstructed states. So just for finishing, we then performed a last experiment in which we monitored the decoherence of a Schrodinger cat state as a function of time. So we basically prepare an even Schrodinger cat state and look at this decoherence as a function of time by reconstructing its Wigner function, or its density operator, at different time delay between preparation, and preparation is detection of the first atom which splits the phase and projects the field on the cat state, and then the measurements which can be delayed to reconstruct the density operator after some delay. So here is the result, this movie of decoherence of Schrodinger cat state. So you see that as a function of time, the well-contrasted fringes we had in between the two components of the cats slowly disappear, and what is left at the end of the movie, the time scale is here, it's tenths of milliseconds. This experiment was performed with the best cavity we had, with a cavity damping time of 130 milliseconds. And you see that at a time scale which is shorter than the energy damping time of the cavity, there is still some information encoded in the phase of the field. The two field components have not collapsed, but the coherence of the superposition is not anymore visible, and it's just erased in the noise. And I put it again, in the initial state of this, you have very clearly visible fringes which disappear much faster than the average energy of the field stored in the cavity. And on this movie, you directly see with your eyes the two different time scales, the decoherence time, which is faster than the damping time of energy in the cavity. So we can make a quantitative analysis of this experiment. I told you that the amplitude of the oscillations here are a measurement of the coherence of the cat state. So we can extract from the density operator the matrix element corresponding to this coherence and look at their decay as a function of time. So as a function of time, you get this curve for the coherence measure from the data. And we fit on the data with exponential fit the decoherence time of 17 milliseconds with some error bar. Then we can go into the theory. So the simple model I presented you give the result, which is indeed a rigorous result, is that decoherence time should be 2 times the cavity damping time divided by the square of the distance between the two components of the cat, and I should have commented this distance, is d square is about 7.5 photons, and for the decoherence experiment, it was slightly larger. The field injected was slightly larger. It was about 12 photon distance. So then we put the number in this formula. We expect a decoherence time of 22 milliseconds, so slightly slower than the measured result. But indeed, my model giving this result was not taking into account the presence of blackbody radiation in the environment, which shortened the decoherence time, because as soon as you add fluctuations, you are faster to destroy the quantum state. So if you look at this paper, they give the expression of decoherence time taking into account finite temperature, and the expected time is 19.5 milliseconds, which is within the error bar the same as the measurement result. So it means that here we not only qualitatively understand decoherence, but we have also very good quantitative measurement of the decoherence time. So I will just now conclude this lecture by showing again the Schrodinger cat decoherence signal. So indeed, we saw 2 different methods for generating a Schrodinger cat state in the cavity. In the first lecture, I considered resonant interaction, which leads also to Schrodinger cat. And indeed, the advantage of the resonance method is that when resonant, the coupling is stronger, and it goes faster to fabricate larger Schrodinger cat state. So in this resonant, the resonant experiment performed with slow atoms, we prepared a Schrodinger cat state with a distance between the two components, which was 44, instead of about 11 or 12 in this experiment. So I conclude here with the Schrodinger cat state and just mention some direction in which this cavity QED experiments are still developing. So the old setup with the fast atomic beam is not used for generating entanglement between two high-Q cavities. So presently we have two very high-Q cavities in the setup, and we were recently able to prepare a first simple entangled state of the two cavities by using an atom. So one photon shared in a coherent way between the two cavities. And the interesting aspect of this is the implementation of an original method for performing state reconstruction. If you have more mode for describing your states, it's more difficult to reconstruct because you need to, the Hilbert states becomes larger and larger, and it becomes very expensive to measure everything about the atom. And indeed, here we implement a method which kind of optimize, which allows to gather information to reconstruct the state, not by using just one atom having interacted with the prepared state and preparing it again, but we can use a chain of atoms and get all the information of a quantum trajectory that you monitor after preparation of the state. And then we have this state reconstruction. Now, Igor Dutsenko, who's in charge of this experiment, is using this setup in the context of quantum thermodynamics by using the cavities as kind of hot or cold reservoir, atoms as tools to transfer energy from one reservoir to the other, and you can play nice quantum games and quantum thermodynamic games with this by using some atoms as Maxwell daemon, allowing you to sort the experiments in such a way that heat goes from cold to warm, and one can check fluctuation theorems about all this. That's the topic developed by Igor Dutsenko. So concerning the slow atom experiment, we perform another measurement I did not presented, which is the spectroscopy of the dress state of the atom in the cavity, which in principle allows you to have a very nice tool to prepare, again, large Schrodinger cat states in a way I did not presented by using what we call the quantum xenodynamics. And quantum xenodynamics is a way to make a classical dynamic, and the classical dynamic is the injection of a classical field in the cavity. It becomes quantum if you add some measurement, not just measurement projecting the system in the initial state, that's the usual Zeno effect which just freezes the evolution, but instead of freezing the evolution, you can measure a state which is far away from the origin and design in the Hilbert space a kind of border that the system cannot go across. And when a classical state touches the border set by the Zeno measurement, the dynamics becomes very quantum. So that's something which can be investigated with slow atom. Another method is reservoir engineering, creating artificial reservoir in order to have the pointer state, the state to which the system converges in steady state, not a classical state, but a Schrodinger cat state. So that's a tricky way to use dissipation as an advantage in order to prepare Schrodinger cat state by using very unusual dissipation. And then we develop in the lab two other topics. So two of them are without cavities, so that's the direction of the experiment. One of them consists in engineering the quantum state of the Rydberg atom in itself by some quantum manipulation technique. So I will talk about this in the colloquium. And the other direction is to build a quantum simulator based on the dipole interaction between Rydberg atoms. So Rydberg atoms are large dipole. They have large dipole interaction. And we are developing a project to trap Rydberg atoms in a structure which additionally suppresses the spontaneous emission. And so this project will be the topic of my last lecture tomorrow. So I guess maybe there are some questions. So I was saying too many things. Yes?
I don't know if I get it right, but how do you vary the alpha?
So from varying alpha, we vary the time, the duration of injection. So we could use attenuator, but attenuator for microwave, you have to rotate something. It's mechanical stuff. The duration, the injection time, you have a microwave modulator, and you can switch on and off the source for a few microseconds or tenths of microseconds, and this allows you to control the amplitude of alpha. So for controlling the phase of alpha, we need also to control the phase of the injection. So it's a little bit more tricky. We could use a phase modulator, electronic phase modulator on the microwave, which was not available when in the lab. So the synthesizer, we had no phase modulation. So we use another trick, which is that the phase is not an absolute phase in the experiment. You have never absolute phases in physics. So the important phase is the phase between injection, which creates the field, which will become the Schrodinger cat state, and the second displacement, which shifts it in phase space. So that's the relative phase between these two microwave pulses, which have to be well defined. And of course, the same synthesizer have to be used for both. It have to be coherent, else you never have the right phase. And then what you have is to shift the phase between the first pulse and the second pulse. And for that, we change slightly the frequency of the synthesizer. And by changing the frequency of the synthesizer, you accumulate between the two pulses a phase shift, which is due to the fact that a frequency-shifted synthesizer is not exactly at resonance with the cavity. So the field you inject initially in the cavity oscillates at the frequency of cavity, whereas the synthesizer oscillates at its own frequency. They accumulate a relative phase, and by changing the detuning between synthesizer and cavity, you can tune the relative phase between the two pulses. Yeah.
In the same idea, how do you empty the cavity? I guess you start again.
So in this experiment, yes, we start again and again the experiment to accumulate a lot of statistical information, and we have to start always with same quantum state. So which means that before injection, we need that the cavity is in vacuum. So we could just wait the decay of the previous experiment, which is long, and we don't like waiting, because when the cavity is good, it means that you have to wait 1 second between two consecutive measurements, which is long. So what we do is actively erase the field of the previous experiment by sending a bunch of atoms in the ground state. Once we have finished one measurement, we put a big sample of Rydberg atoms in the lower state, and which are set at resonance. So they absorb the field, and we send eventually several such samples, which prepare vacuum with very high fidelity, and then we start again a new injection and a new measurement. Okay, thank you.
Sorry, I will do a quick presence check. Adriani Consuelo, Alan Khan,